Good evening. Welcome to Krishna's classroom. We continue from where we left in the last lecture. We introduced the concept of connectedness. And then we stated a theorem which characterizes the connected sets in R. We shall give the proof of this theorem. So let me state the theorem once again. The following statements are equivalent. A, E contained in R, that is E is a subset of R, is connected. Second statement is, for every xy belonging to E and Z that lies between x and y, Z belongs to E. Now the first statement essentially invokes the definition of connectedness. So in a metric space X, let us recall that XD, E is connected if E is the union of two non-empty separated sets, where A, B non-empty and A and B are separate. Sorry, I think I made a slip here. E contained in X is connected if E is not a union of E is not a union of separated What do we mean by separated sets? We say that A, B are separated if A intersection B closure empty and A closure intersection B is these two conditions together. So the conditions are that A and B are non-empty sets, and this is true. Now, what this says is that E is connected if E is not a union of separated non-empty sets. That you cannot find two separated non-empty sets A and B such that E is the union of those non-empty sets. So that is the basic definition that we need to remember. So the first statement that E contained in R is connected. Now what does it mean? What is the negation of that? See, then E contained in R, contained in X is not connected if there exists non-empty which are separated and E is equal to A union. This is not connected. So we shall keep this in our mind. Now the second statement says that here we are specifically, when this is a very general statement. And the second statement is specific for R. So it says for every X and Y belonging to E and Z belonging to R such that X lies between, Z lies between X and Y, then Z belongs to E. Now this you would recall that is also a characterization of an interval. So what it says is that the only connected sets in R are intervals. Now that is the final outcome. Okay, so E, therefore we can sum it up. E okay. I want to make some remarks before I go to the proof of this theorem. Okay, let us look at some examples. In R, we will consider this one. This is obviously connected. So this is, 1, 2. This is obviously the same as 0, 2. It's an interval. Okay. It's obviously connected, and I have tried to write this in the form of two non-empty sets A and B. Suppose I call this A, call this B, then you see that A intersection B is empty. No, what I am going to do is this. A intersection B is empty. Okay. But if I take A intersection B closure, A intersection B closure, that is also empty. And A closure intersection B is non-empty. Okay, so this can be written as the union of two separated sets. So what does this say? It says that these sets 0, 1 and 1, 2 are separated. Okay. Sorry, I think okay, let us take the following example. Minus 1, 0, union 1, 0, 1. This is not connected. Not connected. Why? Because I can take minus 1 A as minus 1, 0 and B as 0, 1, 0, 1, and I have A closure intersection B is empty and A intersection B closure is empty. Therefore, they are separated. So I can write this as a union of two separated non-empty sets. Therefore, is not okay. So let me come back to the example that we were considering. Yeah. So let me just use this space for that. Now we will look at this example, the example that I have considered earlier, namely E contained in R and E I take as minus 1, 0 union 1. And this, you know, is essentially minus 1, 1. So this should be connected. Okay, according to what we expect that this is a connected set. Okay, but how does the definition work? Choose this as A, this as B. So it is written as A union B. Now A equal to -1 0, B equal to 0 1. So you have, if you look at this condition, A closure intersection B is 0, which is non-empty. Okay, although you have A intersection B closure is empty. So these two are two disjoint sets. Okay, these are disjoint sets, but nevertheless they are not separated. So this A and B are not separated. Disjoint. Now clearly, you see, if you take E as then we are able to the union of two separate sets. So you should understand the difference between separated sets and what are called disjoint sets. Every separated sets are certainly disjoint, but disjoint sets need not be separated. Okay, so all these are very basic observations. Now let me say something about the proof of this kind of results. This is a characterization. There are two statements. So our strategy is prove A implies B and B implies, so that A if and only. So that is our strategy. Now a word about this kind of results. We said these two are equivalent. So this statement is equivalent to this in the context of R. Okay, so let me just so one more thing I want to assert is that sometimes we use the negation of statements to prove this. What is the logic of that? Let us understand this. So suppose X is a master set. So this is purely for the sake of students. I mean, you should understand the way in which things are often put. Now, let P and Q be two distinct properties of the elements of so therefore we have so let P capital P designate a set of all x belonging to x such that x just like saying okay, we are talking about subsets of R and we are making a statement that the subset E is connected. Okay, that is one statement. Connectedness we have to see. The second property is say Q. So let us designate by capital Q the set x belonging to x such that Q. Now often we come across statements like P implies Q. That means if a element in X satisfies P, then it satisfies Q also. But something that satisfies Q need not satisfy the statement P. So let us see how the relationship works. So let us consider a statement. Suppose there is a statement P. What does it mean? If X satisfies, that is, if X satisfies P, then it satisfies so every X that satisfies P also satisfies Q. So what is the corresponding relations in terms of these sets? See, this is your master set X and you are talking about subsets of that. Suppose this is P and Q is something given here and we are assuming P implies Q, which means if X satisfies P, then it satisfies Q. So we would have, so this statement is equivalent to saying that P is a subset of Q. Okay, so this is equivalent to saying that is every element X is in capital P implies it is also in Q. That means if it satisfies small p, the condition P, then it satisfies the condition Q. Okay. Now consider this statement. What about the sets? What about the elements that do not satisfy P? It's in P complement. If P, say not P, that's designated by not P. Then what we have is that X does not belong to P, that is X belongs to P complement. Okay. So suppose P is contained in, this is equivalent to saying that Q complement is contained in P complement. Okay, this you know, P contained in implies complement is contained in P complement. Now translate this. Q complement means not Q implies. So you see that P implies Q, this statement is equivalent to saying not Q not P. Therefore, sometimes, see, instead of proving P implies Q, when you want to prove P implies Q, what is that you do? You assume X satisfies P, and then exploit the prevailing conditions on the set, and you come to the conclusion that if that is the case, then X satisfies Q. That is one way. But the other way is, this is equivalent to proving that if X does not satisfy Q, if you are able to prove that if X does not satisfy Q, that means over here X is in the Q complement, then it is in the P complement. So that P contained in Q if and only if Q complement is contained in P complement. Therefore, equivalently you can resort to this. You can assume X does not satisfy Q and then arrive at the result that X does not satisfy. And that is equivalent to saying that P implies Q. So this is just a remark, because this is the sort of techniques that we are going to use in proving this theorem. Okay, now we go to the proof of the theorem. So in this case, we are going to use this negation arguments. Okay. So let me write what we want to prove is, so our first we assume or we prove A implies or equivalently we prove not B implies so instead of proving this, we prove this. Okay, so let us assume that so it is sufficient to prove not A, then that would mean which then means So this is our strategy. So let us start working. Now let me just write down what we mean by the negation of. So assume E is not connected. Assume what we do is assume not B. What is that? So the negation of this statement is that there exists X belonging to E, Y belonging to E, and some set belonging to the open interval xy, which is equivalent to saying x less than z less than y, such that z does not belong to E. So that is the negation of the statement. So first understand that our statement is that for every xy belonging to E and any z that lies between x and y, z belongs to E. Any z belonging to R which lies between x and y, z belongs to E. That's the statement. Now we are assuming the negation of that. The negation of that is there exists some x and y and some z that lies between x and y such that z is not in. Okay. So that's our assumption. Now what do we want to prove? We want to prove not A. So that's our assumption. Claim or is E is not connected. E is not connected. So what do we mean by E is not connected? There exists non-empty separated sets A and B such that E is the union of A and B. So that is what we have to arrive at. So we have to craft the subsets A and B. Let us see how we do it. Okay, but what is given is that there exists some x and some y E. Okay, and a z that lies between x and y in R, which does not belong to x and y belongs to E, but z is something that lies between x and y and it is not in E. That is our assumption. So we have to go from there and construct the non-empty separated sets whose union is the particular set. Okay. So let us start the construction. Define AZ equal to E intersection minus infinity set and B set infinity. So we have defined two sets AZ and BZ. Then we observe what are the properties of these sets. Okay, for that we take some Okay, so first we observe that, then we have first observation is that, you see, since x is less than z, we have x belongs to z and y belongs to z. That is clear. Which implies Bz are non-empty. So we got two sets which are non-empty. Now the second property that we can observe is that, see, AZ is contained in minus infinity by the construction and Bz is contained in infinity. And that implies AZ closure of this is contained in minus infinity z and Bz closure z in. That means these points also get included in this. Okay, because we want to compare, look at AZ intersection BZ closure and BZ intersection AZ closure. Hence, BZ closure empty, and so also AZ closure intersection BZ empty. Okay, that is AZ and BZ are separate. So we have both AZ and BZ separate. Now let me work on the next observation. The third observation is that E is equal to BZ. AZ union BZ. So look at the definition of AZ and BZ. Okay, E is contained. See, you are taking E intersection minus infinity to Z, and BZ is E intersection Z to infinity, and Z does not belong to E. Okay, therefore you see that every element of E is either in AZ or in Z. Okay, therefore this implies E is not connected. E is not connected. That is not A. So not B implies not A. So we have proved that therefore not B implies not A. Or equivalent. So we have proved the first part, that is A implies. Now we want to prove B implies A. So the next statement is now prove and once again we resort to the same art of doing it. What is it? Go to the negations of this statement, and this you know is equivalent to not A not okay. So we attempt proving this. Assume not A, which is the same as is not connected, and we assume and we prove not B. Not B. What is not B? Not B we have already written. Okay. Not B is there exists belonging to E and a Z belonging to the interval open interval AB, sorry, open interval XY, that is X less than Z, such that we prove this. So we start with this assumption. Assume this and we prove this. So let us assume this. So E not connected implies there exists non-empty P which are separated and E is the union of A and B. That is, E is not connected means E can be written as the union of two separated non-empty sets. Okay. So that is the assumption that we are making. Therefore, E is given, and for the given E, you have two non-empty separated sets A and B whose union is equal to. So what we claim is this is the assumption. What we claim is dot B, that is, there exists X belonging to E, Y belonging to E, and some so that is the assumption. That is what we mean by not E. Let us now prove this. So A and B are readily available, A and B are separated. Okay. So what we want to identify is some X and Y in E and some Z in lying in the interval, open interval XY, such that Z does not belong to. Okay. So pick that is possible. Okay, and assume without loss of generality that X is less than 1. Now we have to pounce on a Z which is not in E, okay, but lying in the interval XY. Okay. So we have to construct that. So what we do is we take some hint from here. Okay, suppose you take E equal to say -1, 0, union 0, 1. Okay. we know that E is not connected. Why? E can be written as A union B, where A equal to E equal to 0, 1. With the property that A intersection B closure. What is that? A intersection B closure is empty, and B closure, A closure intersection is also that you can easily see, because this is the A that you are taking. What is A closure? A closure is going to be equal to -1, 0. B closure is 0, 1. Now you take A intersection B closure. A intersection B closure is empty. Okay, because you are taking this and this. And so also A closure intersection B is empty. So what have we done? We are picking some element from here and some element from here. So let us say -12. Why you pick as 1 by 2. And then of course you have x less than. Now we want to show that there exists some number that lies between -12 and +12, which is not in. It's clear. So using take -12 less than 0 less than half, and 0 does not belong to. Okay, so just carefully examine this particular example. Okay, I will also give another example. So E I take as 1, 2, and I take this as union 3. Take this. Okay, I can strengthen this here. Something like, okay, I'm giving a specific example. Okay, now you can easily make this kind of argument. You take A as B as 3, 4, and you can show that E is A and B are non-empty, separated, non-empty, separated, and E is a union of, therefore E is not connected. Here again, one can choose, say, 3 by 2, take x as 3 by 2. There is no sanctity in the choice of, you can choose any element, and even choose 2. And y as, say, 3, 4. So it is 7 by 2. Okay. Now you see that there are lot of elements. So any belonging to 2 to 3, 2 to 3 does not belong to, therefore once again he is not connected. Okay. So how to pick the particular element? I mean, here it is very sensitive because there is only one element that lies. If you pick an x here, if you pick a y here, there is exactly one element which satisfies this criteria, namely 0. So you have to arrive at that. Okay. So how do you arrive at that? This is A, this is B. Okay. So you can see that 0 is the supremum of, okay, you take an A, make an observation. Observation is this. I wipe off this. Soon I will take out the statement of the theorem also. So you see that 0 is the critical element or the unique element that lies between any x and y, x belonging to A and y belonging. Okay, so we have to arrive at that. So in the example 1, lying between x belonging to A and y belonging to B, which is not so how to get hold of this? So what we do is we take to arrive at that, we take A and intersect with the line segment xy. Okay. So if you pictorially, means this. We are taking. Okay, so you are taking a line segment x and y. This is x, this is y. So this is the line segment x. You are intersecting it with this. So what you end up with is x to 0. Okay, so in this case, this is equal to x to 0. Okay, now take the supremum of this. Okay, so the supremum of this one is what? Is 0. So you have to arrive at 0. So supremum of it. So we adopt this technique. So let us do it. It may work in both the cases. I will start doing this now. I remove this. I will return to this example. Just So my strategy is to identify this particular element if possible. I mean, I am not assuming that there is only one element having this property. We are considering the more general situation. So define, so let x belonging to A and y belonging to B, where you have E equal to A union B, A, B, non-empty, separate. This is what we have. And define is the crucial definition. Z equal to A supremum of it's more nice to write as A intersection segment XY. So this is the crucial definition that, okay. Now in some case this particular Z would work, in some case this particular Z will not work, but you will have another element Z1. So let us examine this. By the supremum definition, you see that equation. And that implies Z does not belong to class A closure intersection U is. Okay, that is A and B are separated. This is one of the conditions that we have. In particular, what we can say is this: Z is in A closure, Z may be X itself. Therefore, the possibility is that, see, what we have is X. This is what. Suppose Z does not belong to A, as in that example, 0 does not belong to. Okay. Then what we have is X less than Z less than. Okay. So already Z does not belong to. This one. So what does it say? So Z does not belong to A union B, which is equal. Okay. So the Z lies between X less than Z less than Y, but so you see it is not connected in that case, but it's conditional. So what we have assumed is that if Z does not belong, Okay. Now, there could be a situation where Z belongs to A. Okay. Suppose, for example, I'll just give an example where this could happen. We take the case where B equal to the interval 0, 1. Union, say something like say 3 by 2 can be open up. Then you are taking, to separate this, you are taking this as A, this as B. And how did we define Z? So we had an X here, we had an X picked up from here, Y picked up from. So you had an interval XY. So you had A intersection supremum of this. This is what we have chosen. And this we called Z was defined as this. Okay. Now in this case what happens? Z equal to supremum of, what is your A? A is 0, 1 intersection Y. And what is the supremum here? See, X belongs to A and Y belongs to B and they are separated. Therefore, this is equal to 1 and 1 belongs to, so it could belong to A. We first considered the case where Z does not belong to A and then Z belongs to, by definition, belongs to A closure. So we are considering a situation like this. So suppose Z belongs to A. Then Z does not belong to B closure, because you see that A intersection B closure is, that means does not belong to B. So that, let us save this result. Okay. Now what you have is Z belongs to A, right? But Z does not belong to B. What we are searching for, a Z which is neither in A nor in B. Okay. So let us work on that. How to get hold of such an element. This is the argument that we have. So what I am going to, I will rewrite the whole thing. So my second argument is this. B closure, because A and B are separated. Okay. Right. Now what about this Z? Z belongs to A means actually it is the case where Z belongs to A closure. Okay, right? And A closure equal to A. See, this is the situation that we have considered there. Example, yeah, 0, 1. A is taken as, and 1 is the Z that you are taking. Z belongs to A. And you see, look at the definition of Z. Okay, Z is defined as supremum of this is the definition. Therefore, it could only be at the extreme end. Okay, so this could only be at the extreme end. Then of course, certainly Z belongs to A, Z does not belong to B closure. So you can, there exists a Z1 such that Z less than Z1 less than Y for every Y belonging to B. Why is it so? Okay. Now you see that the extreme case would be, see, Z is a limit point of A and Z is on the boundary of A. Okay. Z is on the sphere. Okay. And therefore that boundary point is not having belonging to, so Z does not belong to B closure. Okay. What does it mean? There is a gap between B closure and A closure. Okay, because the boundary point, see, it is something like this. Z lies at the extreme end of this. Okay. B closure you can take something like this. This is B closure. So this is something here, and see, it is at a boundary point and it is not in B closure, therefore there is a gap. Okay. So Z belongs to A, Z is not in B closure, therefore there exists a Z1 such that Z is less than Z1 less than Y. As you have seen in this example, Z is equal to 1. Okay, in this example, Z is equal to 1. Now you take, and 1 is strictly less than 3 by 2. So 1 belongs to A. Which is equal to A in this case. Okay. Therefore, 1 is not the required element. We have to search for other elements. And because of this condition, Z does not belong to B closure, shows that there is some element in between Z and this 3 by 2 or It is easy to understand. You see, take Z as supremum of A intersection Y and W infimum of B intersection XY. Now you are assuming Z belongs to A. Therefore, it is not in B closure. Therefore, it is not equal to. So, Z is not equal to W. Z is not equal to W. Then you can find some element between Z and W. Say Z1 and Z1 does not belong to. Let's sort of argue. So we will. Okay. Therefore, Z. So there exists a Z1 such that greater than Z and Z1 does not belong to B closure. Or Z1 does not belong to. So Z1 does not belong to A and Z1 does not belong to E, which implies Z1 does not belong to. Let's argue. Okay. So in this case, what you do is, see, this is your Z1. Sorry, Z. Okay. Now, you look at the infimum of that W. This is your W. This is Z. Z is in E, A. W may be in B or may not be in B, depending on whether 3 by 2 is included in that. But in this example, W belongs to B. But then there is plenty of gap between these two. And you can choose any element. In fact, there are plenty of choice now available. And you can put a Z1 dice between this. Okay. Therefore, in this particular case also, in either situation, there exists an element or Z1 such that so this is the alternative. Okay, that is the E is not So what we have proved is that being not connected implies or consequently what you have, this is so that's the proof of the theorem, and you carefully analyze these two examples that I have said, and that will give you an insight into the proof. Thank you very much. So let us conclude our talk today.